Okay, YouTube, this is just a warm-up video that we're going to do here before we start talking about exponential functions. And so we're going to review some basic concepts involved with properties of exponents, starting with just evaluating these four expressions you see here that involve some sort of exponent. And so looking at, say, number one, and I guess through all four here, we want to just pay attention to order of operations. So just recalling that, an expression like this, negative 4 times 5 cubed, we want to go ahead and take 5 and cube it first, and just remembering that when we talk about 5 cubed, what we're really saying is 5 times itself 3 times. And so carrying this out first, I think we get 5 times 5 is 25 times another 5 there. We'd really get negative 4 times a positive 125. So carrying this out, I suppose we'd end up with a negative 500, but this would be our value of our expression there if we're following the order of operations. Speaking of raising to a power, we're going to raise this negative 3 to the 4th power. Now this is a little bit different than negative 3 to the 4th power. If we had written it this way, that would be maybe misconstrued for negative 1 times 3 to the 4th power, where the 4 only applies to the 3, and we interpret this as having a negative 1 out in front. In this particular case, we're talking about we need to take the negative 3 times itself 4 times. And so in doing so, we see that anytime we have a negative times itself an even number of times, of course, we end up with a positive result. And so what we're going to end up with is something that's definitely positive. We end up with 3 to the 4th, so really, I guess it's supposed it'd be 9 times 9 here, so 81. Okay. Now looking at number 3, we have a fraction here, and you'll notice that the negative is out in front. And so if in doubt, write it out. I know it sounds really cheesy, but I suppose what that means is if you're ever having a question about what to do with an exponent, what we can do is we can just rewrite out what it means, and it really means negative out in front, and then we have 7/8 really taken times itself. And so in this particular case, we are going to say that this is like a negative 1 out in front. And so really we'll say negative 1. Now when you square 7/8, really remember rules of exponents here. I just can't seem to write on that there. 7 squared over 8 squared would be the same thing as 7 over 8 squared. And so in this case we get 7 squared, which is 49, over 8 squared, which is 64. And take that times a negative 1, we just end up with something that's opposite in value. So negative 49 64ths. And so for number 4 here, basically the same idea, except for this time let's use our property where it says if we take a quotient to a power, then we'll raise the entire numerator and the entire denominator to that power. And so we end up with 3 cubed, which is our 27 here, and then 10 cubed, 10 times 10 times 10. Suppose we'd end up with 27 1,000ths. So that is how we would want to go about evaluating those. Now for the second part of this, let's go ahead and do something here we haven't talked about in a while, is refer to the domain and range of a function, okay? And identify the domain and range of a function. Remember that when we're talking about the domain and range of a function, okay, we're usually representing this with some t-chart, x and y, but we could also represent it as like an input and an output. And so we say that our input here are x values, okay? These are the ones we often refer to as our domain values. And our output values, these would be our output. Let me write output here. These are our range values here. And so when we plug in an x value, what's happening is through our function here, f, we're mapping an x onto a y. And so I suppose we get all these x-y pairs here. But essentially, when we talk about the domain of a function, let's just refer to its definition here. We say that the domain of a function is the complete set of all possible values of the independent variable, which is our x variable here. So in plain English, this definition means this. The domain is the set of all possible x values which will make the function work and will output real y values. So what we're looking for is what are all the x values that cause our function to work. Now likewise, we're going to be looking for range, which we can look at the definition of range here. The range of a function is the complete set of all possible resulting values of the dependent variable. So that's our y variable. That's what results. But after we substitute all the x values into the domain. So it says after we've substituted the domain. So this one in plain English basically says that the range is the resulting y values we get after substituting all the possible x values. And so when we talk about domain and range, really what we're identifying are what are all the x values and what are all the y values that make our function work, or at least what are all the x values that make our function work and what are all the y values that we get after we plug those in. So we can see that when we're talking about domain, we're really looking at the x-axis here. When we're talking about range, we're really looking at the y-axis here. So looking at this cubic function, looks like a cubic function here, I notice that these arrows basically mean it goes on forever and ever. And so to say that, we want to find which x values cause this to work, I would say that every single x value in a cubic function, all of these x values on this number line are going to cause this to work. So we can say all real x values is how we would state the domain here. And then the same thing with our y values. When you look at the y-axis here, it's going to hit all y values from negative infinity all the way up to positive infinity here on the y-axis. So we say all real numbers as well. So all real y values is our range. Now, these other three examples here are going to be a little bit different. When you look at number 6, the interesting thing here is our function seems to only be defined on this interval of x values here. And so when we discuss domain and range, okay, remember domain is the interval of x values for which our function works. And so our function was always between, I'd say, these two x values right here. And so you'll notice that we have closed dots here. But what I would say is that just indicates that we did use those x values. And so when I say what are these x values, I say from -1 out to a +3. And so the way we're going to write this is we're going to say all real x values such that x is always between -1 and +3. So we would say that these are our domain values here. Now when we discuss range, remember range is all y values. Looking at the lowest this graph ever gets in terms of a y axis, it looks like it gets right here down to a height of -1 and then gets up to a height of right here, I suppose from both sides, gets up to a height of 3. And so we would say that the range of this function is all of these y values on the y-axis here that got spit out when we plugged in these x values into the domain. So it looks like -1 all the way up to 3, which is ironic because we got the same thing for our domain, except for this time we're going to write y. Those are our y values that are restricted there. When you look at something like number 7, a little bit interesting about number 7 is that these are a set of points here. And so I suppose that if we were to represent these as a t-chart, let's write our function out, x, y. Suppose we could say that this point here is the point 1, 5. So 1 maps onto 5. Looks like we have the point 3, 5. So we have 3, 5. Looks like 4 5s also on here. And then 6, 5. And so when we talk about the domain of something like this, it's not continuous, we say. Then what we're going to do is we just represent the domain as a set of numbers. And we say that the domain, all of the inputs for which our function existed were 1, 3, 4, and 6. And as far as our range is concerned, our range, we'd say, well, the range of values that we spit out really was only 5. And you notice we only have to list that once because 5 is the only thing this function spits out. And then lastly, number 8 here, we say, well, I don't know, what do you think about our domain and range here? What are the x values for which our function is defined? And so I suppose if you're looking at this, this is kind of like our first one. Because of the arrows, I can see it goes down forever and ever, but it's also kind of going to the left and to the right as we curve off. So even though it gets steeper and steeper, it looks like it's going to cross all x values. We say all real x values are in the domain. In other words, it's going to hit all x values on the x-axis here. And when we plug all those x values into this function, looks like in terms of y values, we're going to hit on the y-axis here all y values from way down at -infinity up to a height of 0. So the way we're going to write this is we're going to say all y values less than or equal to 0 are in the range of our function. Cheers.